My name is Soumya Ghosh, and this is joint work with co-first authors Samir Deshpande and Nguyen, and senior author Tamara Broderick. Let's say we have some data from an unknown probability distribution that we are interested in analyzing. Depending on the goal of our analysis, we might be interested in either comparing different probabilistic models of this data or comparing different algorithms for fitting a chosen probabilistic model. Now, a widely used approach for such comparisons involves collecting additional test data and computing the test log likelihood. Despite its popularity, however, test log likelihoods can be misleading when the goal of the data analysis is poorly aligned with what the test log likelihood is implicitly measuring. In particular, we provide simple pedagogical examples and clear arguments in this paper which show that better, in other words higher, test log likelihood values do not imply a more accurate approximation of the Bayesian posterior, and that while higher test log likelihoods do indicate more accurate forecasts in a very particular Kullback-Leibler sense, they may not correspond to other notions of accuracy, such as recovering the correct mean or other higher order moments of the data generating process. To make things concrete, let us look at an illustrative example. Consider a data generating process denoted by script P where we draw one-dimensional covariates x sub n from a standard normal distribution and add some heteroscedastic noise to it to generate the responses z sub n. We sample 100 such instances from the data generating process for training and denoted by script D. We sample 10,000 instances for testing from the same data generating process and denoted by script D star. We use this test data to compute our test log likelihoods. Let us further assume that we are interested in performing a Bayesian analysis. To this end, we choose to model this data with a regression model with homoscedastic noise and standard normal priors over the regression coefficients, theta 1 and theta 2. The standard Bayesian workflow then involves computing the posterior over the regression coefficients and computing a predictive distribution, pi of y star, given the training data script D, by marginalizing over the computed posterior. In the slide here, y star denotes a single test instance. Now, in our stylized example, thanks to conjugacy, the Bayesian posterior over the regression coefficients and the corresponding predictive distributions can be computed exactly. The dashed red line in panel A right here shows the mean of the exact predictive distribution, and the shaded region is the corresponding 95% predictive interval. The points in black represent the 100 training instances. In a typical Bayesian analysis in practice, however, the exact Bayesian posterior is rarely available. In such cases, it is common for a practitioner to be interested in comparing different algorithms for approximating the typically intractable Bayesian posterior. To study how test log likelihood varies with the quality of posterior approximation, we approximate the exact posterior with approximations of increasingly poor quality, shown in panels B through F. These approximations all use an isotropic Gaussian distribution to approximate the exact posterior, and we progressively inflate the marginal variances of these isotropic Gaussians as we move from panel B to panel F. Panels B through F show the predictive distributions induced by the corresponding approximate posteriors. As we can see, the predictive variances of the approximations in panels B through F are inflated compared to the exact posterior's predictive variance shown in panel A. And these poorer approximations, especially the ones in panels E and F, end up covering the data a lot better than the true posterior does. For a more quantitative measure, look at the left number in the title of each panel. This is the 2-Wasserstein distance to the exact posterior. The right number in the title is the test log likelihood evaluated on the 10,000 held out test data points, script D star. We see that even though the distance from the posterior is increasing in the 2-Wasserstein sense from panels B through F, the test log likelihood continues to go up. This is further highlighted in the plot on the right, where we plot the 2-Wasserstein distance to the exact posterior along the x-axis against the test log likelihood on the y-axis. We see that in this example, test log likelihood increases monotonically with increasing distance from the posterior, and moreover, approximations to the posterior, poor quality approximations at that, achieve higher test log likelihoods than the exact posterior itself, which is shown in the dashed black line. In fact, in this example, if we were to select the approximation with the highest test log likelihood, we would end up selecting the worst approximation to the posterior. An approximation that is not only farthest in the two-Wasserstein distance, but also according to other reasonable measures of distances from the posterior. In our paper, we redo this analysis but use the reverse scale divergence to measure the discrepancy from the exact posterior, and the conclusions of that analysis remain unchanged. At first glance, the results in the previous slide may seem counterintuitive, especially given the large literature that reports test log likelihoods when evaluating new algorithms for approximate Bayesian inference. To understand why we see this mismatch between test log likelihoods and posterior approximation quality, we first note that model misspecification isn't decisive in general, even though it was a feature in the example shown in the previous slide. In a different example in our paper, we show that it is possible to have a well-specified model where higher test log likelihoods do not correspond to better approximations to the posterior. Okay, now so to see what really is going on, consider the cartoon on the right. Given an approximate posterior pi hat, a common goal is to measure some notion of distance between pi hat and the true posterior pi in a latent parameter space. In many cases of interest in practice, this parameter space would be a high-dimensional and potentially multimodal. In other situations, we might be interested in the data space, where we care about measuring the distance between the predictive distributions induced by the posterior pi and the approximation pi hat, either because this is of interest in itself, or as a proxy to the distance between the posterior and the approximation in the parameter space, which is difficult to compute. However, as it turns out, test log likelihood measures neither of these two quantities. Instead, the test log likelihood can be seen as an approximate divergence between the approximate predictive distribution and the exact data generating process, as we show with the pink line in this figure. Concretely, the test log likelihood forms a Monte Carlo approximation of the negative KL divergence between the true data generating process and the predictive distribution induced by the approximate posterior pi hat. Asymptotically, as the number of test instances goes to infinity, this approximation becomes exact. Thus, there is no real reason for the test log likelihood to align well with the quality of posterior approximation. In fact, the only case in which test log likelihood aligns with the distances between the approximate predictive distribution and the posterior predictive distribution is in the asymptotic limit of infinite training data, and when using a well-specified model, and further assuming various regularity conditions to hold. In this case, the posterior predictive collapses to the true data generating process, thereby aligning test log likelihood to the distance between the predictive distributions. Now, of course, even if this idealized setting was ever available in practice, in the limit of infinite training data, we might expect that there would be no uncertainty left in the Bayesian posterior, and thus no clear reason for performing a Bayesian analysis in the first place. So we saw in the previous slide that test log likelihood approximates the negative KL divergence between the true data generating process and the predictive distribution induced by a model of interest. Based on this, we might conclude that test log likelihood is useful for measuring the quality of forecasts made by a probabilistic model. Indeed, if our goal is to produce predictive distributions close in the KL sense to the data generating process, then TLL is a faithful metric. However, if you care about notions of accuracy, other notions of accuracy, for instance, if you want to know which of the two alternate models recovers the first moment of the data generating process more accurately, then TLL can be misleading. As an illustrative example, consider the two plots on the right. Here we have fed two different Gaussian processes to 100 training data instances between -5 and +5, and evaluated it on 10,000 test instances represented by the black dots. We see that the Gaussian process in panel A better recovers the mean but has a lower test log likelihood than the one in panel B. Finally, to conclude, we emphasize that our work is not meant to be a blanket indictment or a recommendation for the use of test log likelihoods. Rather, we hope to encourage researchers to explicitly state and commit to a particular data analysis goal and use tools appropriate for that desired goal, recognizing that different methods may perform better under different goals. We also provide a couple of concrete recommendations with respect to how test log likelihoods are currently used in practice. First, using test log likelihoods to compare how well different algorithms approximate the Bayesian posterior can be misleading. Better approximations can produce poorer test log likelihood values and vice versa. We recommend not using test log likelihoods for such comparisons. Second, it is fine to use test log likelihoods for assessing the predictive accuracy as long as the goal is to measure closeness to the true data generating process in the KL sense. If this is not an appropriate goal for the application at hand, we recommend reconsidering the use of test log likelihoods.